Hi everyone, let's talk about finding the area of a triangle. Usually when we have a triangle like this one, let's call it A, B, and C, we label one of the sides as B and we draw a height H. And we say that the area of the triangle ABC, we denote it with square brackets like this, is equal to BH over 2. And you can do it with any of the three sides and their corresponding heights. So that's the usual way of finding the area of a triangle. But remarkably, there are at least 5 other ways of finding the area of a triangle, and I'll be showing those to you now. So for the second method, let's say we have an incircle with the corresponding triangle around it. So usually what we do is we draw the triangle and there's always an incircle, although we won't be proving that right now. So let's call it ABC. And what we call the radius of the incircle is the inradius. And we're going to call that small r. And we're going to call the side lengths A, B, and C. And we're going to let S equal to A plus B plus C over 2. And that's the semi-perimeter because it's equal to half of the perimeter. And it turns out that the area of ABC is equal to R times S. And you can do that by breaking the triangle up into 3 triangles like this. And I'll leave that proof to you. So that's our second method. For the third method, it's called Heron's formula. And this one says that the area of ABC is equal to S times S minus A. Again, we're using this definition of S. S minus B, S minus C, and square root over the whole thing. And my favorite proof of this is by a guy named Miles Dillon Edwards. And he published a proof of this using complex numbers, and it's a pretty amazing proof. I recommend looking it up. Our fourth method of finding the area of a triangle can be derived using the cosine law. And what it says is that the area of ABC is equal to half times side A times side B times sine of C. It looks like the sine law, but we actually derive it using the cosine law. So that is how we would find the area of a triangle in a fourth way. And you can do this with the corresponding symmetric variables for the other 2 sides as well. So BC sine A, CA sine B. I'll write that down for you. Half BC sine A equal to half CA sine B. So that's the fourth way. The fifth way involves what we call the circumradius. So if we have a circle like this and inscribed in it is a triangle, and there's always a circumcircle, although we're not going to prove that right now. If we call the triangle ABC and the center of the circle is here and we call that radius capital R, then the area of ABC is equal to ABC over 4 times R. And we prove this using the extended law of sines. So that's our fifth way of finding the area of a triangle. And for the final way, it's one of my favorite. It's quite remarkable. What we do is that we extend the side lengths or sides of the triangle so that we have something like this. So A, B, C. And then we draw what's called the X circles. So we get circles. It's not going to look great because it's better to draw with a computer. But the circles are tangent to these side lengths like this. So we've got 3 x circles like this, and we're going to call the radii. This one is going to be RC, this one is going to be RA because it's opposite to A, and this one is going to be RB. And as before, we're going to have the incircle inside the triangle, and we're going to call the radius of that R. And amazingly, the area of the triangle ABC is equal to R times RA times RB times RC square root over the whole thing. And you can prove this using Heron's formula and formulas for these individual exradii. There's a formula, I believe, in Coxeter's Geometry Revisited for the exradii. So that is our 6th way of finding the area of a triangle. Okay, thank you for watching, and I'll see you next time.